and beyond. The amount of information there was really not much. So we had to actually develop our own testing machine. The machine we proposed for that project was something like this guy, a small roadmilling machine, right? So you can actually excavate the surface in layers. And you can create a trench if you want to. You can create roadways and stuff. So that was the idea, and it could be useful mining. The problem is that for this machine, if you work in different materials, you need different cutter heads, right? You cannot use the same cutter heads in asphalt and in concrete and in fluffy soil. I mean, it has to have different cutter heads, and we don't have that luxury out there. Plus, the issue of size. In order for me as a designer of the machine to have a ton of force for excavation, the mass of the machine had to be 20 tons. That's not a joke. It's really serious. It's a problem because for penetrating that material, hard material, I needed this force anyway. So that was a difficulty that we had to deal with. Nevertheless, we started our testing program. We thought, all right, let's characterize frozen soil and see how it looks like. So this is actually a picture of a frozen simulant. We don't have regolith because that size regolith would be probably buying half of the properties in Boulder. Okay, we don't have regolith. We had simulant. We put it, mixed it with different amount of water, and ran the test. As you can see, it breaks exactly like rock. The minus 130, 40 degrees Celsius, degrees Celsius there. You see, it's breaking exactly like rock. So we had done a bunch of tests, and of course, these are the stress strain curves. And ultimately, we said, all right, if we go with about almost saturated simulant, we could get to about 6,800 psi, about 50 megapascal. That's quite a bit. For us rock guys, not, but for you civil guys, it's a lot, right? 50 megapascal is something to deal with, right? We did additional testing for penetration. This is actually 0.5% or actually 0.6% water. This is 11% water. Penetrating into that material was difficult. This is 0.5% water. If you go to about 12 millimeter penetration, we need a 25 kilonewton, 2.5 tons. It's not a joke, but it's still, okay, you can think about it. But for 11% water content, look at the force. 200 kilonewton, 20 tons. Boy, that's a bummer, right? So looking at all this test data and whatnot, we concluded that an analogous to a frozen regolith could be this saline limestone. So for all the tests in room temperature, we actually use the same saline limestone, okay? So what did we do? We actually took a block of saline limestone that was actually about 5 feet wide, 6 feet long, 2 feet high. We started cutting it. We first did what we call linear cutting test, cut it in line with different spacing. So change the spacing between the cuts to see if we can actually cut the material. And you can see if the spacing is too small, you make a lot of fines. It takes a lot of energy. Energy deployment in that material, it means that it could actually evaporate the water. So it's not really wise. If the spacing is too large, if you get good chips, that's a good achievement. But, oh boy, you have to penetrate just enough to make the chips pop up. So we did a lot of tests and came up with the result. This is the bit we used, not a dull bit, a very sharp bit with a very sharp nose. And of course, the trade-off is that the life of the bit may be lower. That's the bit we used, and these are the results. So for different spacing between the cuts, different depth of penetration, and that bit, we measured the bit forces. So 200 pound, 300 pound, 500 pound, and so on. Okay, that's not bad. It's doable. This is the vertical load. This is the side load. This is the drag force. The drag force actually is the force that determines your power requirement. So not bad so far, right? So these are the variation of forces versus penetration and so on. So we need it for model. Next step was to actually do a rotary cutting test. We built a cutter head. We put a bit here and started cutting the surface of the rock. Again, these are pictures of the rotary cutting head, and the tools are instrumented, so we could measure the forces. Okay? And we did a lot of tests. And the question here was that how fast can we actually mine it? And how deep of a threshold we can mine? So we did a bunch of testing here, and we got some confirmation. Again, the rock you see here is that limestone block, huge block. Based on that, we came up with a design of a cutter head for the first time ever, which is like an accordion, so it can actually expand or contract. It's really crazy. So it's really neat mechanical system, has these bits on these plates, and actually works out like an accordion. This is the side view. You see complexity with a very neat planetary gear system. And feast your eyes. This is how it looked like at the end. We build it. This is at its expanded condition. And now, oops, this is the contracted condition. See the difference? Okay, and we did some tests with it on grout, and then ultimately on the rock. Again, you can see at the end of a run. So this is a sort of medium strength grout to represent low water content. This is higher water content, and you can see expansion and contraction of the cutter head. Ultimately, we came up with this production estimate based on the material strength. Remember, we're going to about 50 megapascal with 7,000 psi. So the estimates are for a 10 kilowatt machine. I mean, you cannot joke around with 5 or 10 watts. I mean, let's be realistic. 10 kilowatt is something that's doable. So if we are in low moisture content, we can get about 510 cubic meters per hour. In harder material, we're down to about 2 cubic meters per hour. And for all the estimates for operation on the moon, these are reasonable if we can get operations going. So we're thinking about how to mount this on the system. Okay, do we put it in the center of the machine and whatnot? But ultimately, we came up with this plan. Remember this Chariot from the earlier slide? So this is an existing Chariot. So we're going to actually put this in front with a loading mechanism to dump it into some boxes to give the machine the mass, and then start excavating. And the boxes would actually get transferred to another Chariot to go to the processing plant for extraction of the water. So this project finished a few years ago. This is our current project, drilling on the moon. And not necessarily just drilling. What we're trying to do is to characterize the material as we're drilling. So we don't want to take samples. We want to be able to actually drill and on a real time know what the heck is going on down there. Are we in frozen material? Are we hitting a rock? Or is it just soil compacted, right? So that is our ongoing project. It is based on a project that I finished for National Institute of Occupational Health and Safety. In this project, we're actually working in underground mines, drilling into the roof, because you put roof bolts anywhere, in the tunnel or in the mine. It's part of the process. So what we wanted to do is to record the machine parameters, analyze it, and find out for every hole, what is it that we're cutting and where the joints are. Then build that all into a geological model, right? So that was the concept. We took that concept now, we are actually trying to do the same thing for NASA. So anyway, this is a busy slide, don't expect you to read it, but here is what we are doing now. We continued characterization of the regolith to find out how do the material property change with temperature and moisture content. And then try different modes of excavating, cutting it. Okay? We've already developed a drill, you will see it. And then based on these two and the data that we get from the drill, we want to see what is the material we're cutting. And the theory was, and is, that a strength of the frozen regolith correlates with water content. So if I can measure a strength, voila, I can tell you what is the water content, right? And in our previous project, we have actually proven that drilling parameters can tell you what the strength is. So we are halfway there. Right now what we are doing actually compressive strength testing, tensile strength testing, and everything. For this particular project, we have made this gadget, which is a steel contraption. We put the sample here, and the whole thing is submerged in liquid nitrogen. So it takes it down to minus 196, and then in the process it stabilizes around 190, minus 190. And we do a stress strain curve and measure compressive strength. Now, this is the first set of graphs, going from minus 190 to minus 130. Look at how the strength changes. So it does change, and actually allows us to monitor the temperature and have that in our back pocket. But the beauty of it is here. This is variable water content. From 0, we didn't go 0, because 0 is just powder. It doesn't even hold up, right? 369. Remember 369? Okay, so this is the median estimated water in the permanently shadowed crater, right? Plus minus 3. So we actually covered that bit. And see how beautiful it goes up. So it gives us a very good direct linear correlation between water content and strength. So that is established. So we looked at all the drills that have been designed and deployed: Crooks, Icebreaker, Data, and PR, Resource Prospector. And based on this, developed our specs for our drill. So this is the schematic of our drill. It's already built. And it's a rotary auger drill. We have a 1 kilowatt motor. Is overpowered. The actual machine is 300 watts. Ours is 1 kilowatt, but we are monitoring the power, and at one point we're limited. And the rest of the specs, this is again, schematic and the sample. We've already made a sample of regolith with micro cement to mimic the, let's say, frozen water. And this is the machine with the different components. And of course, so we just cast something in hydrostone, and I don't know why they put it on a pallet, so that thing is just juggling around, and everybody goes like, why is this moving so much? Because it's on a pallet. Anyway, I don't know why they took the movie like this, but anyhow, the drill is actually operating right now, and we are going to drill into a frozen, a simulated frozen regolith, which is actually with micro cement. Get base data, and then we'll make a layer cake with the same material but different cement ratios to get different strength that mimics the different water content. So we'll do a bunch of these blocks and try to get as much data as we can to actually develop the correlation between machine parameters, drill parameters, and strength. And from strength we get to water, right? But getting there, that information is not as easy as it may look like, because as you drill down, the bit starts wearing, it changes the machine behavior. The material that's coming up on the auger will absorb some of the energy, so you have to account for it. As you go deeper, you have to make adjustments. So actually, we're using machine learning algorithms, AI, to actually come up with that relationship. Okay, that's about it. Be glad to answer your questions.
I have a quick question, please. Can we still apply the basic and the fundamental of soil mechanics and geotechnical engineering that we learned here on this planet on different planets?
Yes, we can. If the conditions are the same, we can. But what the issue is that the conditions are not the same. See, most of the problem